A number of maritime accidents have occurred in seawaters around Japan over the past several years. Most of these accidents resulted from the seafarers' poor or wrong understanding of weather and sea states peculiar to seawaters around Japan. For safe navigation, it's quite important to properly understand the characteristics of weather and sea states. It's especially important to have good knowledge of rough seas caused by tropical and extratropical cyclones and the topographical features of Japanese ports. This video will focus on weather and sea states which are very important for safe navigation in the sea waters around Japan, and on the characteristics of major ports and bays in Japan. The term air mass refers to the homogeneous air mass that covers a vast area for a long period of time. Air masses change seasonally and influence the climatic changes in the regions covered. Japan is located in the mid-latitude, where the vast Eurasian continent meets the Pacific Ocean, and its climate is strongly influenced by several air masses that change seasonally. Two major air masses exert great influence on the Japanese climate. They are the Siberian continental air mass, a cold, dry polar continental air mass, and the North Pacific tropical air mass, a warm, humid tropical maritime air mass. In Japan, the North Pacific tropical air mass is also called the Ogasawara air mass. Furthermore, in spring and autumn, the Yangtze River air mass, a warm, dry, migratory tropical continental air mass, and the Okhotsk Sea air mass, a cold, humid polar maritime air mass, exert a strong influence on the Japanese climate. Finally, there is equatorial air mass, a tropical maritime air mass that is carried with typhoons. In total, 5 air masses strongly influence the Japanese climate and sea waters. Energy for the generation and development of an extratropical cyclone is the potential energy difference between a warm air mass in a low-latitude region and a cold air mass in a polar region. Let's take a look at the 4 stages in the life cycle of an extratropical cyclone: the generation, development, mature, and attenuation stages. The generation stage. In the region from the eastern coastal region of the Chinese continent to the East China Sea, there exists a stationary front formed by a polar continental air mass in the north, the so-called Siberian continental polar air mass, and a tropical maritime air mass in the south, the North Pacific tropical air mass. As the atmospheric pressure trough at the upper level approaches from the west, the surface atmospheric pressure in the area under the eastern part of the trough tends to decline. This tendency for the air pressure to decline creates counterclockwise airflows on the ground, then generates an extratropical cyclone having active warm and cold fronts. The center of the surface air pressure depression and that of the upper air pressure depression incline to the west. The development stage. As the upper-level pressure trough moves eastwards, the front undulates dramatically and unstably. The extratropical cyclone passes in the vicinity of Japan as it continues to develop. The warm front is formed in front of the cyclone and extends from the center to the southeast due to the northward movement of warm air, and a cold front is formed behind it, extending from the center to the southwest due to the southward movement of cold air. The mature stage. The central air pressure of the extratropical cyclone reaches its minimum in the sea east of Japan. At this stage, the front begins to be occluded and forms the occluded front. This is when the force of the extratropical cyclone reaches its peak. the attenuation stage. The cyclone approaches or almost reaches the waters around the Aleutian Islands, and the front is completely occluded. At this point, the lowest centre of the upper-level pressure is almost above the centre of the surface cyclone, and the cyclone becomes an isolated air eddy, without fronts, and is completely merged with the cold air mass. The extratropical cyclone begins to attenuate and finally dies out. The blocking phenomenon is often observed in the area of the Aleutian Sea in winter. It is a phenomenon by which a cut-off high, produced in the upper air, is located at the front of the extratropical cyclone and blocks the eastward migration of the cyclone. Its migration blocked, the cyclone may, however, maintain its intensity. This results in rough seas for a prolonged period. Therefore, you should pay attention to the blocking phenomenon when you draw up a navigation plan to such areas. In winter, extratropical cyclones may rapidly develop in the region from east of the Nojimazaki Point to the western North Pacific Ocean. In this sea area, the Kuroshio Current raises seawater temperatures. Isotherm lines extend from west to east, and seawater temperatures are higher in the south than in the north. Meanwhile, upper-level cold air protrudes southward like a wedge or tongue towards the cold front of the surface low and travels from west to east along the easterly migration of the cyclone. When upper cold air comes southwards like a wedge over the waters off Nojimazaki Point, where water temperatures are high and the temperature difference between the cold air and warm seawater becomes greater as the cold air moves southwards, ocean waves tend to increase in height. Because of the significant temperature differences between seawater and the cold air in the area behind the cold front, the sea waves off Nojimazaki Point are prone to be larger than usual. Sometimes, an extratropical cyclone, passing over or near Japan, develops rapidly, and its central atmospheric pressure drops by more than 20 hectopascals a day. This type of cyclone is named a bomb cyclone in Japan because its intensity is strengthened explosively. This type of cyclone usually emerges in early spring. Since it can cause rough weather and sea conditions worse than expected, for the safety of your ship, you must pay close attention to it. Tropical cyclones refer to cyclones generated in tropical or subtropical waters. The generation of a tropical cyclone requires a continuous supply of water vapor energy. Tropical cyclones are formed in sea areas where sea surface temperatures exceed 26 degrees Celsius. Generally, this means tropical cyclones are formed in sea areas between 5 and 20 degrees latitude, excluding equatorial waters. Northeast and southeast trade winds in the northern and southern hemispheres blow into the equatorial areas and form a trough known as an equatorial trough, or intertropical convergence zone, or ITCZ. An ITCZ usually migrates westward while undulating north and south. When this undulation becomes unstable and increases, it forms an eddy that develops into a tropical cyclone. The energy source for a tropical cyclone is the latent heat of water vapor that is discharged when humid air rises, is cooled, and then condenses into droplets. Rising warm air is less dense than the surrounding atmosphere due to latent heat, and it continues to rise. This lowers the central atmospheric pressure of the tropical cyclone and keeps the cyclone developing. tropical cyclones have no fronts because they are generated amid a homogeneous tropical maritime air mass that is warm and humid. The tropical cyclone is called by different names, depending on the region where it's formed. In the western North Pacific, it's called typhoon, or taifu in Japanese. In the eastern Pacific and the Gulf of Mexico, it's called a hurricane. And in the Indian Ocean and the western South Pacific, it's called a cyclone. In general, it's called a tropical cyclone. The tropical cyclone is classified internationally by the degree of its intensity. It's ranked from its weakest to its strongest stages as tropical depression, tropical storm, severe tropical storm, and typhoon. The international definition of a typhoon is a storm with a maximum wind speed exceeding 64 knots, that is, the wind force of 12. You should note that the Japan Meteorological Agency defines typhoons as a tropical cyclone with a wind speed of 34 knots or more, that is, a wind force of 8 or more. Typhoons are huge atmospheric eddies with diameters ranging from hundreds to thousands of kilometers. Inside the eddy, strong updrafts form cumulonimbus. The eye of a typhoon is formed by a downdraft at the center of the typhoon, and the heaviest rain and strongest wind are encountered below the eye wall. In the vicinity of the tropopause, above the eye of a typhoon, an eddy of cirrus clouds is formed that flows outwards, clockwise, due to the Coriolis force, an effect of the Earth's rotation. Side semicircles, and the performance capability of your ship. When the typhoon is likely to approach while anchoring or loading or unloading cargo in a port, take every possible evacuation action well in advance by collecting and analyzing weather information as well as following the harbour master's instructions. The Japanese archipelago, surrounded by the sea, is blessed with a number of natural harbours. Unique topographical features give each of these harbours their own distinct characteristics. Seasonal changes in winds, waves and tides also vary, so it's important for safe ship operation to understand well the characteristics of these harbours before you arrive. In this section, we will explain the characteristics of 3 main bays and 1 port in Japan: Tokyo Bay, Ise Bay, Osaka Bay, and Kashima Port. While foreign ships that have not completed procedures for entering the ports are not permitted to anchor, they are allowed to enter the bays for anchorage by obtaining permission of the Japan Coast Guard in emergency cases, such as stormy weather and equipment trouble. Ship enters the Uraga Middle No. 6 light buoy area of the Uraga route under a strong northerly wind, and during the ebb tide, the ship is prone to drift southwards. In the worst case, ships may find themselves off course. Most of the routes leading to berths in the bay are affected by sideward tidal currents. Such tidal currents flow at a right angle to the route, and current speed reaches as high as 0.8 knots at some points. So when a ship navigates at a slow speed, she tends to drift sidewards. In particular, strong sideward tidal currents, faster than 0.5 knots, can be seen along the Kawasaki, Negishi, Kimitsu and Futsu routes. You should also be aware that the port in Kurihama Bay is directly affected by tidal currents as well as northerly and southerly winds. Berths affected most strongly by the sideward tidal currents are the East Wharfs A and B of JFE Steel Corporation in Kawasaki. Daikoku Wharfs L, C3 and C4 berths, located near the Tsurumi River mouth, are always affected by river flows, which are strengthened during and immediately after heavy rains. Furthermore, strong northwesterly winds in winter can cause ships to drift suddenly, affecting berthing and unberthing procedures. Since the LNG tanker berths in the Sodegura district protrude like a comb, they are subject to a sideward tidal current. We have a report that incoming ships have had their bows swung in unexpected directions when entering one of the comb-like berths. As such, we recommend you to keep eyes open for unexpected currents. The KOC berth is located 3 miles off northwest of the shoreline, so ships approaching and berthing KOC berth are strongly affected by irregular tidal currents. The direction and speed of tidal currents vary according to depth. When berthing a deep draft ship, safe navigation requires that a lookout boat reports the state of these currents. If a typhoon or a developing cyclone approaches the berth, a ship may need to leave the berth and find refuge in the bay to avoid the storm. Prepare yourself in advance by asking your agent or other reliable person for advice on a suitable anchorage. Some places, like Nakanose, cannot be used for anchorage without prior permission. Secure your anchorage through someone such as your agent and confirm whether you can anchor there during stormy weather. Shown here are 2 AIS displays of the bay. One is a normal situation taken a few days before a typhoon's approach, and the other shows locations of anchoring ships during a typhoon's passage. Even if your large ship can anchor away from other ships, it's likely that smaller ships will come very close to your anchored position later. Therefore, prudent judgment is required for safe anchorage. Considering anchoring and traffic conditions in Tokyo Bay, it's advised that large ships should evacuate the bay when they have enough time. For anchoring, a sand seabed or hard mud is ideal. In Tokyo Bay, however, the seabed characteristics in the inner part of the bay differ from that of the bay entrance in the south. In the northern part of the bay, the seabed is mud, while in the southern part the seabed is made of rocks and gravel, covered by 1 to 3 meter layers of sand and mud. This means that the risk of a dragging anchor is higher in southern waters off Kisarazu and Futsu, and in Nakanose when strong winds blow. To avoid dragging anchor, a 2-anchor mooring is recommended. Even if anchor cables become fouled, you can avoid cutting the anchor chain by using a tugboat. In the vicinity of the pilot station, 2.5 miles south of the Uraga Buoy No. 1, wind, waves and swells are rough when southerly winds are blowing. In this area, the water depth can suddenly become shallow. This topographical feature causes swells from the open sea to grow larger. Please note that when southerly wind speeds exceed 20 meters per second and the wave height exceeds 4 meters in this area, it is often difficult for a pilot boat to come down to the pilot station. Ise Mikawa Bay is surrounded by land. It has a water depth of about 35 meters and its seabed is mud, making it suitable for anchoring. Indeed, it is a good natural harbour, protected from rough seas outside. The maximum tidal current speed in the Irigo Channel is 2.7 knots. Current directions are approximately 330 degrees during the flood tide and 150 degrees during the ebb tide. The difference between directions of the tidal current and navigational route is about 20 degrees. The tidal current in the western half of the channel flows into the inner part of Ise Bay, while the current in the eastern half of the channel flows into Mikawa Bay. The tidal current speed flowing into Mikawa Bay is higher than that flowing into the inner part of Ise Bay. When the Irigo Channel is at flood tide, the current becomes a northwesterly stream flowing from the open sea towards the inner part of Ise Bay. As the flood tide reaches the Ise-1 No. 3 light buoy north of the Irigo Channel route, a part of the tidal current turns its course towards Mikawa Bay in the northeast. When ships navigate the Irigo Channel route, the current effect is low, but when they go past the route, ships sometimes drift eastwards. The current flow becomes faster in winter when the flood tide combines with strong northwesterly winds. It's useful to note that ships, especially pure car carriers, navigating southwards from Nagoya port, can find themselves drifting towards Ise-1 No. 3 light buoy as they decelerate under the speed restrictions imposed in the Irigo Channel route. The ebb tide is a southeasterly current, and in addition to the flow towards the bay mouth, a southwesterly flow from Mikawa Bay towards Kamishima Island is produced in the vicinity of the Ise-1 No. 3 light buoy. During ebb tide under strong easterly winds, northbound ships tend to drift westwards towards the Ise-1 No. 3 light buoy. This should be remembered. When the strong northwesterly monsoon blows, the Ise-1 No. 2 light buoy will sometimes drift about 70 meters to the southeast. When a ship approaches the No. 2 light buoy in the weather side at a low speed, she blocks the wind, and the buoy tends to return to its original position. As a result, the buoy approaches the ship. Beware of this phenomenon. Strong wind blowing through the channel, also known as Nakanishi, is the winter monsoon peculiar to Ise Bay. Nakanishi refers to the wind that blows from the valley to the channel when northwesterly winds have strengthened due to the typical winter atmospheric pressure distribution. That is, with the high to the west and the low to the east. The wind speed of the Nakanishi can exceed 20 meters per second at sea. It's said to blow as far as 50 to 70 miles off Cape Irigo Misaki. The north to south distance of the region from Wakasa Bay to Ise Bay is the narrowest in the Japanese archipelago. This region is located between mountain chains to the east and west, and this is the passage of the winter northwesterlies. Many of the anchorages in Ise Bay have a water depth of some 35 meters with a flat seabed of mud, offering good temporary anchorages. You can minimize the effects of winds and waves by anchoring in the eastern part of the bay when easterly winds are strong, and in the western part under strong westerly winds. Suitable anchorages for large ships are the southern part of Ise Bay, off Toshijima Island, off Tsu Matsuzaka, the central part of Ise Bay, west of the central part of Chita Peninsula and off Cape Nomozaki. While these anchoring locations are advantageous relative to easterly or southeasterly winds because they are behind islands, you should pay attention to a number of fishing reefs in the waters around Toshijima Island. The most suitable location is the sea area to the west of the line drawn at an angle of 307 degrees from Kamishima Island, which protects ships from typhoon-induced winds and swell. However, the risk of dragging anchor rises significantly under the reverse gale known as fukikaishi, that is the strong wind in the opposite direction after the passage of a typhoon. Meanwhile, the area some 3 miles north of Ujiyamada port is not suitable for anchoring because of its gravel seabed. Vessels seeking refuge during rough weather and guided by a pilot usually anchor off Toshijima Island or off Tsu Matsuzaka. The southern side of Ise Bay sea berth is suitable for anchorage, except under southerly winds, when ships are prone to drift towards the sea berth. Do not attempt to anchor a large ship near the sea berth during rough weather. Atsumi Bay is surrounded by land in all directions and is an ideal anchorage in rough weather, mostly for medium to small size vessels. Osaka Bay is surrounded by land and is a good natural harbour protected from the open sea. The depth in the eastern half of the bay is 17 to 20 metres and the seabed is mud, making it suitable for anchorage. The depth in the vicinity of Awaji Island in the western half of the bay is some 50 metres and is not suitable for anchorage. Tidal currents are concentrated at Tomogashima Channel, and the current speed is very swift. In fact, it's so strong in the central part of the channel that a deep trough has been carved on the seabed. Generally, tidal currents 5 meters below the surface are recorded in the tide table, but it's thought that the tidal current speeds vary significantly according to depth. In the vicinity of the Tomogashima Channel, seabed contours are not uniform, so tidal currents are not uniform either. A strong current is encountered at greater depths. Be aware that deep draft vessels are affected more by tidal currents. When the tidal current flows southwards or northwards, a current flows through from the east on the eastern side of the channel and causes ships to drift westward. You should pay attention to this current effect when you maneuver a ship with a draft of more than 10 meters and at speeds of less than 12 knots. In the deep central part of the channel, you will encounter upwelling currents from the seabed, which remain quite strong even when the tidal current is weak. Be aware that these currents make it difficult for you to maneuver your ship. Tidal currents are particularly strong in the waters several miles north and south of Tomogashima Channel. To be specific, the strong current runs from the light buoy off Sumoto in the north to the point 3 miles south of Okinoshima Island, where pilots usually disembark. Tidal currents become markedly weaker in sea areas more distant than these. For the bay as a whole, the strongest current flows in the area between Tomogashima Channel and the water east of Akashi Kaikyo Strait, its maximum speed being 1 knot. The speed will decrease to less than 0.5 knots as you move eastwards or westwards from the current. When the Tomogashima Channel current flows northwards, the current in the Akashi Kaikyo area flows westwards. When the Tomogashima Channel current flows southwards, the current in the Akashi Kaikyo area flows eastwards. Inside the bay, the current is weak and flows slowly clockwise, having no discernible impact on ship handling. In Osaka Bay, in addition to the influence of the clockwise current, you will encounter westerly and northwesterly winds in winter along the Hamadera route. Be aware that ships navigating this route are prone to drift sidewards as a result. When storms pass over Osaka Bay, many ships can find good anchorages in the areas northeast and southwest of Kansai International Airport. The eastern part of Osaka Bay is suitable for anchorage, where its depth is about 20 meters and the seabed is mud. On the other hand, the depth in the western part of the bay near Awaji Island is about 50 meters, making it unsuitable for anchorage due to the risk of dragging anchor when easterly strong winds are blowing. Osaka Bay does not have specific anchorage zoning for large ships and medium and smaller vessels. However, large ships tend to anchor in the deeper side of the 20-meter depth contour line, while medium and smaller vessels anchor in shallower waters. In many cases, medium and small vessels anchor in waters near the shore northeast of Kansai International Airport, where it's shallower than the 20-meter depth contour line. The seabed of this anchorage is hard clay, favourable anchoring ground, and very few cases of dragging anchor and stranding have been seen even during typhoons. In rough weather, pilots lead their ships to anchor at locations away from the main route from Tomogashima Channel to Kobe and Osaka ports to ensure safe navigation of other ships that will enter the bay bound for Osaka port after the typhoon has passed. When rough weather leads to all ships in port being ordered to leave, medium and smaller ships usually anchor in waters northeast or southwest of Kansai International Airport. When large ships are ordered to leave the port and have to seek shelter from rough weather, they should contact their agents or other reliable parties for advice and evacuate the bay in advance. Since the Kashima port entrance faces northeast, the port is affected by winds and waves from this direction. The port is protected from the open sea by a single breakwater, so when rough weather is anticipated, it's recommended to leave the port quickly. Anchorages also face the open sea, where rough waves are generated during a storm. Sailing out to avoid rough seas is recommended, rather than anchoring when a developing cyclone or typhoon is likely to approach and pass through the area. A tidal current of a maximum 0.5 knots runs near the entrance of Kashima Channel. When a developing cyclone migrates northwards along the eastern coast of Japan's main island, Honshu, strong northerly or northeasterly winds begin to blow. These in turn lead to northerly or northeasterly swells 4 to 6 meters in height, which produce a strong drift current that flows offshore along the central breakwater. You will frequently encounter pyramid-shaped irregular waves at Kashima International Port between autumn and early spring. Northerly or northeasterly winds tend to blow often during this period. Therefore, waves tend to be higher in shallow waters from buoy number 1 at the port entrance to the breakwater. In particular, when a developing cyclone passes through the area south of Boso Peninsula, you will encounter large swells from the south even after the cyclone has passed. If strong northeasterly winds are blowing at the same time, irregular waves, such as pyramidal waves, are prone to occur. In the afternoon of October the 6th, 2006, when a rapidly developed extratropical cyclone passed over the Kashima-Nada Sea, a 190,000 deadweight-ton ship loaded with iron ore was swept by strong winds and drifted due to a dragging anchor. Finally, she was grounded on a shoal. The ship's hull was broken into 3 parts and 10 crew members lost their lives. In response to this tragedy, guidelines for safe navigation at Kashima port were drawn up, and the standards for the issuance of an evacuation alert and official liaison were established. The purpose of the evacuation alert is to ensure that ships evacuate the port before a developed cyclone arrives. An alert is issued at least 24 hours in advance when an oceanographic forecast indicates that the average wind speed will exceed 10 meters per second, and wave height in directions between north and east will exceed 4 meters. Specifics of the alert are: 1. Ships of deadweight ton 3,000 or more shall evacuate the port. 2. Ships of deadweight ton 3,000 or more anchored outside the port shall immediately raise anchor and evacuate to safe coastal waters. 3. Ships less than deadweight ton 3,000 anchored inside or outside Kashima port shall moor along the quayside or evacuate to another port or berth upon discussion with their agents. Alert announcements are timed as follows. The first alert, the preliminary warning, is issued 3 hours before the second alert. The second alert, the alert for evacuation, is issued 6 hours before winds are forecast to reach gale strength, and ships over 3,000 deadweight tons are asked to evacuate the port. Kashima port faces the open sea, so ships must leave the port to avoid rough seas and may have to travel a great distance in search of a safe place to wait out a storm. The second alert recommendation is issued with advance notice to allow ships sufficient time to find refuge. In normal weather, ships usually anchor in waters around 5 miles from the edge of the breakwater. Because the anchorage faces the open sea, ships should pay due attention to changes in weather and sea surface conditions and take prompt action when rough weather is expected by leaving the anchorage and evacuating. Rough weather during voyages. Meteorological information can be obtained from the following sources. Weather charts distributed by the Japan Meteorological Agency. Typhoon course forecasts available for free on the internet, and weather information supplied for a fee by weather information companies. Weather information from the internet and companies is useful when you work on the evacuation plan, because both provide estimated typhoon courses at least a week in advance. Here we will introduce the various weather charts issued by the Japan Meteorological Agency and show you how to use them. Usually, weather charts refer to surface weather charts that show weather conditions on the Earth's surface. On a surface weather chart, isobars for each 4 hectopascals are drawn with 1,000 hectopascals as the standard. The chart is published every 6 hours. Let's review the symbols used on surface weather charts to indicate typhoon-related information. Typhoon warnings are issued in 3 stages and relate to the wind force of the storm zone. Tropical cyclones are displayed in 4 stages according to maximum wind speed. Tropical cyclones that have a maximum speed exceeding 64 knots are defined as typhoons. In Japan, tropical storms, or TS, with a maximum speed exceeding 34 knots are defined as typhoons. Name, location, and other information of the typhoon are shown here, which is represented by concentric circles. For example, T0705 Usagi 0705 indicates that it's the fifth typhoon in 2007. The figures 0705 in parentheses are a global identifier number. Usagi is a name assigned alphabetically from a predetermined list. The inscription of a typhoon also indicates the reliability of positional information. For the example shown on the screen, the typhoon's current position is latitude 24.2 degrees north and longitude 137.9 degrees east, and the reliability is good. Good means that the margin of error for the position of the typhoon center is less than 30 miles. Fair means the margin of error is more than 30 miles but less than 60 miles. And poor means the margin of error is more than 60 miles. Other information indicated on the map includes the course direction, the maximum wind speed at a typhoon center, and the spread of the storm zone. Forecast circles are used to indicate specific zones the typhoon is likely to reach as time progresses. This display method is for forecasting the course of the typhoon as well as a cyclone, for which the gale warning has been issued. Wave charts issued by the Japan Meteorological Agency are Ocean Wave Nowcast Chart, 24-hour Ocean Wave Forecast Chart, Coastal Wave Nowcast Chart, and 24-hour Coastal Wave Forecast Chart. The Nowcast and Forecast wave charts display equal wave height lines, composed of meter-by-meter heights of significant waves and swells, along with prevailing wave directions, anticyclonic and cyclonic central positions, and fronts. AWPN refers to the North Pacific Ocean Wave Nowcast chart, for which date and time are displayed in universal time. The example here is a chart showing wave conditions on October the 4th, 2006 at Universal Time 00 hour. Taking into account risks to smaller vessels, it uses caution to indicate sea areas where wave heights exceed 4 meters, using bold lines to show 4-meter and 8-meter wave heights. The outlined arrow on the wave chart indicates the prevailing direction of wave propagation in the sea area concerned. Waves propagate in the direction of the arrow. From this example, you can see that the prevailing waves are propagating from northwest to southeast. FWPN refers to the North Pacific 24-hour ocean wave forecast chart. In this example, from the date and time inscription, we can determine that this is a 24-hour wave forecast covering October the 7th, 2006 at Universal Time 00 hour through October the 8th, 2006 at Universal Time 00 hour. Ships navigating high-wave sea areas risk damage to their cargoes and hulls, leading to significantly reduced speeds and potentially significant delays to their voyage plans. You must take proper safety measures by accurately grasping sea surface conditions along the direction of your ship's course, using the 24-hour ocean wave forecast chart and other resources. An outlined arrow in a white circle indicates the anticipated direction of wave propagation. The number assigned to it represents a forecast value for wave cycle in units of 1 second, The first decimal place represents a forecast value for significant wave heights in units of 1 metre. As such, this example forecasts north-northeasterly waves with a cycle of 11 seconds and wave heights of 2.3 metres. When it comes to upper air charts, 850 hectopascals, 700 hectopascals, 500 hectopascals and 300 hectopascal charts are available. The average altitude for each chart is 1,500 meters for 850 hectopascals, 3,000 meters for 700 hectopascals, and approximately 5,400 meters for 500 hectopascals. Constant pressure surfaces are almost flat in the east to west direction, but there are some inclinations and unevenness in the south to north direction. Constant pressure charts express such inclinations and unevenness as altitudes. Commonly known as upper air charts, these charts show the altitude distribution of constant pressure surfaces. This corresponds to the barometric pressure distribution on surface charts. Solid lines on a 500 hectopascal upper air chart are contour lines, and they are shown for every increment of 60 meters. Broken lines are isothermal lines, and they represent increments of 6 degrees. The 500 hectopascal upper air chart is the most important chart because it shows atmospheric flows and tendencies of atmospheric pressures and temperatures in the troposphere, the intermediate region of the atmosphere. In the northern hemisphere, winds blow in parallel with contour lines, looking to higher altitudes on the right. In areas where lines are more congested, winds blow more strongly. A typhoon forecast circle forecasts the typhoon's center position after a certain amount of time has elapsed. The circle indicates the area to which the typhoon's center is forecast to advance. The size of circles are not uniform, varying according to the accuracy of the forecast. Generally, a small circle indicates that the typhoon's advance direction is stable, whereas a large circle suggests that the typhoon's course is complicated and unpredictable. The example shown here indicates a 70% probability that the typhoon's center position at the time of the forecast will move into the forecast circle. A storm zone refers to a range where strong winds of average speeds exceeding 25 meters per second are presumed to be blowing. The storm alert zone around the typhoon forecast circle identifies the area that will enter the storm zone if the typhoon's center advances into the forecast circle. Using our accumulated experience, we will now show you a yardstick for forecasting typhoon courses. Since a typhoon moves with sustained power, significantly accurate forecasting is possible for successive 12-hour periods by tracing and extending the typhoon's current course. Understanding that after deflection, a typhoon tends to advance along contour lines of the 500 hectopascal upper air chart, expect it to move more rapidly when gaps between the contour lines are narrow. A weak typhoon can be forecast using the 700 hectopascal upper air chart. Should a typhoon that takes an irregular course emerge, the subsequent typhoon is also likely to take an irregular course. Typhoons tend to advance towards warm sectors. If there is a cold section in front of them, they tend either to be stationary or deflect. Typhoons tend to advance towards areas of the greatest atmospheric pressure decline or toward a contraction field. Ships' crews must strive to gather these weather charts and take proper countermeasures well in advance, taking into account their ship's performance capabilities as well as the force and scale of the rough weather expected to be encountered.